In this video, we look at molecular geometry, the three-dimensional spatial arrangement of atoms in molecules. And we do this using the valence shell electron pair repulsion model, or VSEPR, to help us predict the shape of molecules. And we're also going to use Lewis structures to help with this. Now, we've seen previously that Lewis structures can give us an understanding of molecules in terms of the order of attachment of atoms, the number and type of bonds present in a molecule, and they're also able to represent both the bonding and non-bonding pairs of electrons that exist within molecules. They do not, however, give us any indication of the overall shape of a molecule, and that is its molecular geometry. In fact, Lewis structures falsely imply that molecules have a flat two-dimensional geometry, as you can see from the Lewis structure given for ammonia at the top of the screen. Here we have three other representations of the ammonia molecule, which can actually give us a much greater appreciation of the overall three-dimensional geometric shape of this molecule. Nevertheless, despite the shortcomings of Lewis structures, we can still use the information present in a Lewis structure to determine the molecular geometry or the overall shape of a molecule. And as I said, we're going to do this using a model called the valence shell electron pair repulsion model, or VSEPR for short. The VSEPR model predicts shapes of molecules and ions by assuming that valence shell electron pairs within molecules are arranged around each atom to minimize the repulsion of electron pairs. In other words, the bonding and non-bonding pairs of electrons around atoms are kept as far from each other as possible. So for example, in this figure we can see that when two pairs of valence electrons surround the nucleus of an atom, they will arrange themselves to be on opposite sides of the nucleus. Under this arrangement, the electron pairs are as far from each other as possible and the repulsion is minimized. This gives a linear arrangement of electron pairs with the angle between them being 180 degrees. When three pairs of electrons surround a nucleus, they will arrange themselves in a plane towards the corners of an equilateral triangle. The resultant shape is referred to as trigonal planar, and the angle between the electron pairs is 120 degrees. Four pairs of electrons around an atom lead to a tetrahedral shape, with the angle between the electron pairs being 109.5 degrees. When five pairs of electrons surround an atom, three of them are arranged in a trigonal plane, with the angle between each being 120 degrees. The other two pairs sit above and below the plane at an angle of 90 degrees from the trigonal plane. The resultant shape appears as if two triangular pyramids are attached at the base, and the name of this arrangement is called trigonal bipyramidal. An octahedral geometry is obtained when six pairs of electrons surround a central atom. Four of the pairs are arranged in a square plane, with the angle between each being 90 degrees. The remaining two sit above and below the square plane, also at an angle of 90 degrees. To determine the geometric shape of a molecule, we need to locate the position of the atoms and not the electron pairs. So as an example, let's consider the ammonia molecule again, NH3. The Lewis structure shows an octet of electrons around the central nitrogen atom with a total of four pairs of electrons, three of them bonding pairs and one of them a non-bonding pair of electrons. We have just seen that the base geometric shape around an atom that has four pairs of electrons is a tetrahedral shape. However, the ammonia molecule only has three atoms attached, and the shape is derived from the position of the atoms and not the position of all of the electron pairs. In this case, we can see that the shape of the molecule is actually a trigonal pyramid, with the three hydrogen atoms forming the triangular base and the nitrogen atom forming the apex of the pyramid. Even though all four pairs of electrons repel each other in a tetrahedral shape, the actual shape of the molecule is somewhat different. In fact, the presence of the non-bonding pair of electrons is actually responsible for pushing the other three atoms into the trigonal pyramid shape. So being able to identify the number of bonding domains and the number of non-bonding domains around a central atom is therefore important in being able to determine the overall molecular shape. Now we can use this table as a guide for determining the molecular geometry of molecules, so long as we know the total number of electron domains, as well as the number of bonding domains and the number of non-bonding domains. Now you will note that this table refers to the number of electron domains rather than electron pairs, and this is because in determining molecular geometry, multiple bonds, that's double bonds or triple bonds, are treated as if they were a single electron pair, or more correctly, a single domain of electron density. So, for example, the Lewis structure for carbon dioxide shows a central carbon atom attached to 2 oxygen atoms via double bonds. This gives a total of 4 bonding pairs of electrons around the central carbon atom in accordance with the octet rule. In terms of the geometry of the carbon dioxide molecule, however, each of these double bonds is considered a single domain of electron density. The 2 domains will arrange themselves to be as far apart from each other as possible, leading to a linear arrangement of electron domains with the angle between them being 180 degrees. The carbon dioxide molecule is therefore said to have 2 bonding domains and 0 non-bonding domains, since there are no non-bonding pairs of electrons on the central carbon atom. And this leads to a linear geometry according to this table. So the shape of a carbon dioxide molecule is a linear shape. Where an atom has a total of 3 electron domains surrounding it, 2 possibilities exist. All 3 domains are bonding domains, or only 2 are bonding domains and the other one involves a non-bonding pair of electrons. An example of the former is the BF3 molecule with 3 bonding domains and 0 non-bonding domains. In other words, there are 3 bonding pairs of electrons around the central boron atom and there are no non-bonding electrons on that central atom. An example of the latter is the nitrite ion, NO2-, which shows 2 bonding domains, and remember the double bond is considered a single bonding domain, and there is 1 non-bonding domain arising from the lone pair of electrons. In the case of 4 electron domains around a central atom, the molecular geometry can take on 3 possible shapes. Tetrahedral, when all 4 are bonding domains, trigonal pyramidal, when there are 3 bonding domains and 1 non-bonding domain, and bent, when there are 2 bonding domains and 2 non-bonding domains. The common examples shown for these 3 geometries are methane, ammonia, and water. And all 3 of these molecules have 4 regions of electron density, but only the methane molecule has 4 atoms attached to the central atom, giving it the tetrahedral shape. Ammonia has 3 atoms attached with 3 bonding domains and 1 non-bonding pair of electrons, giving it a trigonal pyramidal shape. Water has 2 atoms attached to the central atom and 2 non-bonding pairs, giving it the bent shape. In the case of 5 electron domains surrounding a central atom, this table shows that there are 4 possible molecular geometries. Trigonal bipyramidal, where there are 5 bonding domains and 0 non-bonding domains. The seesaw or distorted tetrahedral shape, when we have 4 bonding domains and 1 non-bonding domain. The T-shape, when we have 3 bonding domains and 2 non-bonding domains. Or a linear shape, when we have 2 bonding domains and 3 non-bonding domains. In the case of 6 electron domains surrounding a central atom, this table shows that there are 3 possible molecular geometries. The octahedral shape, with 6 bonding domains and 0 non-bonding domains. The square pyramidal shape, when we have 5 bonding domains and 1 non-bonding domain. Or the square planar shape, where we have 4 bonding domains and 2 non-bonding domains. So the steps required to predict molecular geometry using the VSEPR model can be summarised as follows. We need to draw the Lewis structure from the molecular formula given. We need to identify and count the total number of electron domains around the central atom. And remember, double or triple bonds count as a single electron domain. We need to identify the number of bonding domains, and we need to identify the number of non-bonding domains. Bonding domains will be associated with atoms, and non-bonding domains will be associated with non-bonding pairs of electrons. We then obtain the molecular geometry from the direction of the bonding domains using the information provided in the tables just shown.